My dear students, in the last class we have to prove some properties of cosets, and this class is also we try to solve one or two more theorems, and then if we have a time permits we have to start the Lagrange's theorem, or we have to define the index of the subgroup and G, and we have to so let's start with the theorem. Let G be a group and H is a subgroup of a G, then any two right cosets of H in G have the same number of elements. We have the last class, we have to show that means if we have a number of elements, this is one correspondings, that the map is from bijective. So we have to show that if we have any two right cosets of a subgroup H in G have the same number of elements. So we using the same technique for proving this result. We have to take a two right cosets, and then between these two right cosets we have to define a map, and then we have to try to show that that map is a bijective. If this map is a bijective, then we can simply say that the number of elements of these two cosets are the same. So let G1 and G2 be H of G1 and H of G2 be any two right cosets of H in G. Then we have to define a map H of G1 is equal to H of G2 by F of H G1 is equal to F H of G2. Now first things we have to, if we have to define this map, so we have to show that this map is a well defined. If this map is a well defined, and then next we have to show that this map is a 1 1, and then we have onto. So if we have to show that this map, we have to define this map is 1 1 and onto is bijective. So that means we can say that the number of elements of a HG1 and number of elements in the HG2 have the any two right cosets of H has a same number of elements. So let's say start with the showing that this is equal to uh, uh, first is defined is a well defined. So take F is a well defined, we have to take H of H1 G1 and H2 G2 are the element of H of G1, and we have to just say that we just taking in this form H1 G1, we take a H2 and G2, and this is the element of H of G1, this is the element of H of T2. Now this implies that we have to just say that we take a H of G1. So we have to take a H of G1 and H2 G1 by G is the element of a, you know that this clearly this G1 is the element of a G, and G1 is the element of a G, means G1 inverse is also the element of a G. So this can be written as a H1 G1, and then we have a G1 inverse is equal to H2 G1, and then we have a G1 inverse. Now using the associativity condition H1 G1 G1 inverse, and then similarly is equal to we have a H2 G1 G1 inverse, and this is the identity element, or this is the identity element. We have to show that clearly. This means we say that H1 is equal to H2. If H1 is equal to H2, and then we have a G2 is the element of a G, and H is the element of a, you have a H. So we can say simply in the form of this. So this can be this implies that this can be written as a H1 G2 is equal to H2 G2 multiplied G2 in the both the side, and now H1 G1 is equal to H1 G2 is equal to, if we have a f of H1 G1 and H2 G2 is equal to, you have a f of H2, and then you have a G1, and now we have to show that if we have to taking the, if we have a two elements H1 G1 is equal to H2 G2, then we have to show that f of Hg1 is the same as the f of images also function. So if the elements are the same, then the images also they have a same element. So we can say that in this way, can say that the map we have to define is a well defined. Now, and our next objective for this is we have to, if this map is a well defined, so we have to next show that is a injectiveness. That means we have to take any two element h of g1 is equal to f of h g1 is equal to f of h g2, h1 g1 is equal to h2 g2, and then we have to show that the h1 and h2 are the same. So let's prove that f is injective. So we have to clearly say that we have to by this we have to take f of h of g1 is equal to f of h2 g1, and now by the definition this is equal to h of h1 g2 is equal to h1 g2, and now we have to just say that g2 is the element of a g and g2 inverse is also the element of a g, or by applying the, because this is a group and group is hold the cancellation property, so we can use the cancellation property. This implies that h1 is equal to, you have a h2. So we can simply say that if we take a f of h1 g1 is equal to f of h2 g2 g1, then we have to ultimately show that h1 is equal to h2. If h1 is equal to h2, so we can say that this means we have to, therefore h1, so if h1 is equal to h2, this implies that h1 g1 is equal to h2 g1, and then we have to show that if we take f of h1 g1 is equal to f of h2 g2, then we have to show that h1 g1 is the same as a h1 h2 g1, and then we simply say that if these two hold, then can we say that f is a injective. So that means we have to show that f is well defined and f is injective. Now last part of this we have to show that this f is onto. So for onto-ness we have to just or we have to onto-ness we have to take given any element h prime g2 h h g2, and this for some h prime is the element of h, and then we can find a corresponding h prime g1 belongs to the h of g1 in such a way where f of h prime g1 is equal to this h prime g2. Now if we find such an element in this way, so we can simply say that every element of a h of g2 is the image of a some element in h of g1 under f, and that establish that f is surjective. So we can simply say that we take any element of h g2, and then we can find corresponding element this h of g1 h g1, and then we show that f of this element of h g1 is the same as the element of h of g2, and then this means we can simply say that every element of h of g2 is the image of some elements in h of g1 under this f, and that establish that f is a surjective. So we have to show that we have a map is defined from, we take a two right cosets, and then we have to define a map, and this map is well defined and is also injective and also surjective. So it satisfies the all this means we can say that simply they say that this establish this theorem say means any two right cosets of H in G have the same number of element. So if you have to show the bijective, then the number of element in the both the right cosets have the same. Next theorem is saying that if we have a G be a group and H is a subgroup of this G, then the number of left cosets of H in G has the same as the number of right coset in G. So now we have to say that if we have any subgroup of G, then the number of left cosets of H in G and the number of right coset of H in G are the same. So we have to again, if we have to saying that if we have to showing that the number of a left coset and the number of a right cosets are the same. So again we have to prove the method of disproving the same. We have to take one function and we have to define a function from left coset to the right coset or right coset to the left coset, and then show that we define a map, and that map is a bijective. If it is matched, is a bijective. So we can say that if hold the bijectiveness, then we can simply say that that the number of left cosets and the number of right cosets in this any so is the same number. So let's prove. I just denote as LH and RH denote the left and right cosets of H in G. So we have to denote, and then we can define a bijective map f of left to right. This is f of left coset to right coset. Then we have to simply say that by define into form of this G of H. If G of any element of a G of H is in the element of a LH, and then we have to, this map is a map to in the form of a RH. So this can we have defined in the for f of G of H is the form of a H of G inverse. Because we take a G is the element of a G, then always G is a group, so G inverse is always the element of a G. So we can we define in this form, and now we using the one theorem. If you remember, we have to say that if AH is Hg1 is equal to Hg2, then this implies that G1 inverse G2 is the element of H. If and only if condition hold, by this we can easily prove that this is a map. First we have to try to show that this a map is a well defined, and then next step we have to show that this is a clearly this map is a injective, and then surjective, and then finally if it is automorphism, then we have to simply say that the number of element in the left coset and number of the elements of the right coset are the same. So let's first we try to prove that is equal to this is equal to, we have to take a G1H and G2H are the two elements, G1H and G2H is the same. Then we have to show that f of G1H, f of G2H are the same. So now by the result, if you remember, we have to check that G1H is equal to, we have a this is I just proved for a right coset. Now we have to using the left coset, I just said trivially. So this is if and only if condition, we have a G2 inverse G1H is equal to H. And now if you remember, we have to prove that G of H is equal to H, then this implies that G is the element of H also. So there is a this is the theorem. We have proved that there is a 4 A, B, C, D parts is there, then you have these two parts we have to prove that. Now because we have to taking the form of a G1H is equal to G2H, so by that theorem we can say that clearly we can say that G1 inverse and G2 inverse is equal to H. So by first we using this result, so by this we can say that G2 inverse and G1H is the same as a H, and now we using this theorem G of H is equal to H, this implies that G2 inverse G1 is the element of H. And now if G2 inverse G1 is the element of H, then this H can be written as a some G2 inverse, and you have a G1, and then we have to write as a G2H can be written in the form G2 and G2 inverse and G1, and the similar way we have to write this. So we can say that this can be written in the form of a this and this. If this is whole, then we can say that if this is whole, this implies that G1 and G2 inverse G1 is the element of a H. Now if we have to this one again we have to write this A is the element of a sorry, G is the element of H, implies that you can say that H of G is equal to H. So this can be written in the form of we have to write H of G2 inverse G1 is equal to H by this result. So if H of G1 inverse G2 inverse G1 is equal to, we have a H, then we have to H of we have a G2 inverse, then we have a G1. Look right, we write into the form of this H of G2 inverse G1, and then we have to write G1 inverse is equal to H of G1 inverse. And now by using the we associativity here, so we can write H of G2 inverse, then we have to write G1, and G1 inverse is equal to H of G1 inverse. And now this is identity, so we have to show that H of G2 inverse, that is implies that H of G1 inverse. And now H of we have to take in the form of H to GT inverse is equal to H of G1 inverse. And now if you see, we have to define in the form of this f of G of H is equal to H of G of inverse. And now if this is nothing but this is equal to f of we have to f of this can be written as a f of G2H is the same as a f of G1H. And then if we take a G1H is equal to G2H, then we have to show that f of G1H is equal to f of G2H. And then if we show that f of G1H is equal to f of G2H, then clearly the map we have to define this GH is equal to H of G inverse is a well defined. So first part we have to clearly show that this map is clearly is a well defined. Now next part we have to show that map is clearly is a injective, and then finally we have to show that is. So now let us try to prove that, demonstrate that F is a injective. So if for injective we have to again take a this we have to map is defined in the form of this f of GH is equal to H of G inverse. So we take some f of G1H is equal to f of G2H, and then by by this we have to this is equal to, then this is equal to written H of G1 inverse. This implies that H of G2 inverse, and then we have a f of G1 inverse a G2 inverse. Then again use the property which says that we have to use if H of G1 is equal to H of G2, and then this implies say that we can say that H of G2 inverse of G1 is equal to H. So H of we can reuse the property is equal to, so we can say H of G1 G inverse is equal to, so this can be simply write in the form of like this. If we have a this, then we have a if and only if the condition is this H of G1 G2 inverse is equal to H. And then if we have a H of G1 inverse and H of G2 inverse is the same, then this can be by this theorem this can be written in the form of H of G2 inverse, and then or you can just simply, if this is are the same, then we have to write in this form. We have to write H of G1 inverse, we can use multiplied by G is equal to H of G2 inverse, and we have a G1, and this is H of we have to write as a G1 inverse G is equal to H of G2 inverse and G1. And now we have to just say that this is identity. So finally we have to write in this H is equal to, we have a H of G2 inverse and G1, and now you just say that H of G is equal to H. This implies that G is the element of H. By using this result, we just say that if this is equal to H, then G2 inverse G inverse is the element of H. So if we have to this implies that we can say that simply is equal to H of this is the element. So we can say that simply this whole we have to say that is the form of a G2 inverse and G1 is the element of H. And if G2 inverse G1 is the element of a H, then this any H can be written in the form of a G2 inverse and G1, and we have to just say that is the form of this can be written in the form of a G2H is equal to G2 and G2 inverse and G1, and then this can be written as a G2 inverse, and you have a sorry G2 into I just explain you a little bit no places. So we just write into the form. So if we have a G2 inverse and G1 is the element of H, then there exists some H can be written in the form of a G2 inverse and G1, and then we have to write is a G2H can be written as a uh, simply this. So if G1 is the element of a this is the element, therefore G1 is the element of a G2H. This shows that G1 H is equal to G2H. So we can by the other way we can multiply it by G2 from here. So G2, and we have a G2 inverse and G1, and then we can say that simply is this form. So G1 is equal to G2 we have to getting, and then proving that the set is injective. So we have to clearly show that if we have to take a f of G1 H1 is equal to f of G2 H2, f of G1 H is equal to f of G2 H2, then we have to show that G1 H and G2 H are the if the images are the same, then the element are also the same, then we clearly show that this is a injective. Now finally we have to show that this set map defined is surjective. So it is clear that the map F is also surjective, since H G inverse is the element of a right coset. So we have know that because we have a map is defined is equal to left left coset, so left, so we have a right. So this means we have to clearly we have to just say that or just we just write in this form. We have a RL2, we have to RH, and then this is the element of a HG inverse, HG inverse, then you have a G of H, and this means we have to just say that HG inverse is the element of H. Then if we take a F of G inverse H, and this is giving you a simply is equal to H of G inverse ka inverse, and then you know that this is equal to Hg. So clearly we have to show that there exists therefore if Hg inverse is the element of a some element for the right cosets, then we take a of this some f, and G inverse H is equal to as the element of a Hg. So we getting in the form. So this means F is clearly is a surjective, and then so we have to the map is defined is clearly is a bijective. If this map defined from RL to RH is a bijective, so so this means the left coset to the right coset, then the number of a left coset and the number of a right cosets are the same. So we can say simply say that if any we have a then left elements of a left coset and the right coset are the same. We have to prove it this way. Now I just say that one more theorem. We just say that this is a very trivial result. We can say that if H is a subgroup of a group G with G is the element of a G, then Hg is a subgroup if and only if G is the element of a. So in general Hg is not a subgroup, but we can say that Hg is a subgroup. GH is a subgroup if and only if G is the element of a H. So we have a, if G is the element of a H, then we can so for Hg is a subgroup means we have to show that if G is the element of a H, then we have to show that this Hg is a non-empty. So first we show that this if we have a G is the element of a H, then G is the element of a H. So we can show that this means G can be written as a we can say that G can be written as a you have a E of G, and then this is the element of a because this G is the element of a H. So this is the element of a whole is the element of a H. So we can say that this the Hg. So at least identity elements into this. So we just start Hg is a subgroup, then it contains an identity element. If we have to show that Hg is a subgroup, then if Hg is a subgroup, clearly at least one identity elements are there. So if our identity elements is there, then we have to show that this Hg intersection of this identity is clearly is non-empty. So this means this is clearly is not non-empty. We have to show that there is a theorem if we have a any two subset left cosets or the right cosets of these, they are either identical or have a no common elements. So if this clearly, if identity is there, then intersection is equal to not empty, then the only possibility is there, this hg can be written as a h of e, and then h of e is equal to, you have a h, and then when you show that, you know that the result, if hg is equal to h, this is if and only if g is the element of h. So by using this result, we can say that if clearly this is non-empty, if it is non-empty, that there the theorem is saying that hg and h and hg is the sorry, this is we can take h of e. So if hg and hg hg and he intersection is clearly is non-empty, if it is non-empty, then they are equal, and then they equal, f hg is equal to h of e. If hg is equal to he, then we can say that this means he is equal to, you have a h, and then by using this result hg is equal to h, we have to show that g is the element of h, then g is the element of. So if we have show that if hg is a subgroup of a g, then g is the element of h. Now for the converse part, if g is the element of a h, then if g is the element of h, then we have a result, again if and only if we have to say that hg is equal to h. And you say that if hg is equal to h, then hg is equal to, you have a character he, and then hg and he are there is two different clearly, and then by this result we can say that if hg is a sub because this is hg is equal to h, and h is clearly, you have a h is a subgroup of a g, and this hg is the same as a h, so this means hg is also is a subgroup of a g. So this complete the proof of a this result. So we simply say that if you have a any subgroup of a g, so hg or gh, and then we can say that this same result hold for gh is a subgroup if and only if g is a subgroup of a g, if and only if we have to just say that if and only if this g is the element of a this h. So this g is the element of h, then clearly g of h is the element of h, then g of h is the belongs to the h, and that is h is a subgroup. So this means clearly we have to share that this is equal to subgroup. So because again we have to if we have multiplied by the left coset or right coset, if the result is hold for a right coset, then automatically is hold for a left coset also. So we simply say that in this we correctly so all the results I prove in this properties of I take a right cosets, but the result is tree value hold for a left coset also. So similar proof we have to in place of a right coset, so shifting by the left coset. So this all the results hold in this also true for the in the case of a left cosets. So I have to discuss all the various property, and this very helpful when we have to discuss the some of the problem of this cosets. So this complete the portion of cosets, and now we have to move to the our next topic. The next topic is very important topic about the Lagrange's theorem. So in the next class I will start to the by the definition of a index, and then we have to try to prove the Lagrange's theorem, and then some important application about the this Lagrange's theorem. So now I have to stop today's lecture here. Thank you.